Hi, welcome to our lesson over polynomial graphs. So we're just going to be looking into what are polynomial graphs. So first of all, we're going to start by comparing these two graphs to the left with the two graphs to the right. Polynomials look like the first two, not the second two. So what does that mean? And let's get rid of that green that's not supposed to be there. What does that mean? Graphs of polynomials have to be continuous. They are continuous. You know, when you think of quadratics, cubics, those are polynomials that are continuous. So this graph right here, see how there's a big gap from when x is, let's just say 1, and when x is, let's say 2. There's a huge gap in the graph from when x is 1 to x is 2, and we do not have that in a polynomial. So this is a graph to the right. It's a function, but it's not a polynomial. Polynomials also are smooth and they have rounded curves. There are no sharp turns. We call that a sharp turn, believe it or not. We call that a sharp turn even when we are doing calculus. So that's a general look into what polynomial graphs look like. What else do we need to know? We also can discover some things based on whether we're looking at an even degree polynomial or an odd degree polynomial. And so even degree, I mean like y equals x squared, y equals x to the fourth, right? Odd degree would be y equals x cubed, y equals x to the fifth, and y equals just x, like x to the first power. That's an odd degree. And so we notice there's a pattern, right? These even degree graphs, if we look at the right and left hand behavior, the end behavior, we can see that even degree graphs are either going up to the left, up to the right, or down to the left, down to the right, right? And odd degree graphs are either going down to the left, up to the right, or up to the left, down to the right. So we're going to take a closer look at this, and we're going to use Desmos to help us to understand what's going on. So behind this first orange rectangle, you're going to see some even graphs. Y equals x squared, y equals x to the fourth, y equals x to the sixth. And it's really interesting when you look at it. If you want to have fun, get on Desmos, just desmos.com, of course. Get on Desmos and do like y equals x to the 10th, y equals x to the 20th. And it's just shocking. They all, when you're looking at what the end behavior is as x is going far to the left, they're just shooting up. Another way to say this is as x is approaching negative infinity, the function is approaching positive infinity, right? And then as we look at the end behavior, as we go to the right, we notice that the function's also going up. A more technical way to say it is as x is approaching positive infinity, the function's approaching positive infinity. Let's look at what happens when we put a negative, so we're back over with this lime green rectangle. What happens when we put that negative in front of an even degree polynomial? It just flips. We know transformations. We know negatives are going to flip. And so if you've got an even degree polynomial, you know that the left-hand behavior is going to be down and the right-hand behavior is going to be down as well. And then we can compare this to the odd polynomials, right? I want you to even notice that, see, we have y equals x to the fifth plus 3x squared. It doesn't matter if there are other exponents in the polynomial. We look at the highest power polynomial, and it's going to follow this rule, right? If you've got an odd polynomial, it's going to, when we look at the left-hand behavior, it is heading down. When we look at the right-hand behavior, it is heading up. And then, of course, we would expect when we put a negative in front of odd-powered polynomials that pattern is going to flip, right? Because the whole thing flips. So instead of to the left going down, to the left-handed behavior is going up and the right-handed behavior is going down. Do you need to memorize this? Of course you do. So pause this and write it down in a way that you can remember. All right, so we're going to use what we just learned to describe the left-hand and right-hand behavior of this. Now, once again, you could describe it in a more formal way. Instead of saying left-hand behavior, you could say as x is approaching negative infinity, the function is blah, blah, blah. Instead of saying right-hand behavior, you can say as x is approaching positive infinity, the function is blah, blah, blah. But we like this shorthand, left-hand and right-hand behavior. So yes, it is a even, but there's a negative. If there wasn't a negative, the left hand would be going up and the right-handed behavior would be going up. But it's negative and it's flip, boop, down, down. We see an odd, our highest power is an odd power. We're expecting this to be, as we're looking at the left-hand behavior, where graph's going down, right-hand behavior should be going up. Indeed. All right, so why are we looking at this? Well, we're going to be graphing polynomials, so we needed to know, A, that polynomials are designed with smooth curves. Your polynomial shouldn't look all, with straight lines. It just has smooth curves. There are no abrupt spaces, right? There are no gaps. There are no sharp turns. And now we also know that what the end behavior of the graph is going to do based on its highest degree and its leading coefficient. So if its leading coefficient, right, is negative, the pattern gets switched, and if leading coefficient is positive, the pattern stays the same. All right, so now we're going to use everything that we know to sketch a polynomial. So we're going to first look at the highest degree and the leading coefficient. So we're going to see the highest degree is 3, the leading coefficient is 1, but more importantly, the leading coefficient is positive. We know that the left-hand behavior is going to be down and the right-hand behavior is going to be up. This is going to help us as we graph this function that we really don't know what it looks like, right? We can't use transformations. We just don't know what it's going to look like. But we do know it's going to be smooth with curves, and the end behavior to the left is going down and behavior to the right is going up. Now, zeros are a really important thing when we graph, and when we say zeros, and in this case real zeros, so we're not looking at imaginary zeros yet. Real zeros are, that's another way of saying, let's see, I want to make this a little thinner so I can write. Real zeros just refer to our x-intercepts. And the reason why we call them zeros is whenever we set the function equal to 0, we're going to see our x-intercepts, all right? So what we're going to do is we're going to factor. We're going to factor out the GCF, and then we're going to factor the trinomial. So when I look at, first of all, x cubed plus 4x squared minus 12x, I want to know, hey, where, instead of writing equals y, I'm going to write equals 0, because we want to know where is this function equal to 0. Where is y equal to 0? Well, of course, that's going to be on the x-axis. So I'm going to go ahead and factor out the GCF. I'm going to factor out the x. So I end up with x squared plus 4x minus 12 equals 0. And then I'm going to factor some more. I've got a quadratic trinomial that I can go ahead and set up my 2 parentheses, right? I've got to think of 2 numbers that multiply to equal negative 12 and add to equal 4. And what, plus 6 minus 2? That sounds good. All right, I'm running out of space, so I'm going to flip it over. What we're going to use next is the multiplicative property of 0 that says if you have something times something times something, you can be as many somethings as you want, that basically means that each one of those things could equal 0, right? It's kind of like that game. If I had 2 numbers, one in my right hand, one in my left hand, and am I hiding them from you? And I say, hey, if I multiply the number in my right hand times the number in my left hand, it equals 0. You would know right away, well, wait a minute, either the number in your right hand is equal to 0, or the number in your left hand is equal to 0, or maybe even both of them. So that's the idea that we're using right here, the multiplicative property of 0. So we can set x equal to 0, x plus 6 equal to 0, and x minus 2 equal to 0. And when we solve, we get where the graph intersects the x-axis, right? So think about it. 0, 0, I'm going to come and put that dot right there. This means when x is 0, the function's value is 0. Another way of saying that is when x is 0, y is equal to 0. Same thing with that negative 6. 1, 2, 3, 4, 5, 6. I'm putting that on negative 6 because I know that when x is equal to negative 6, y is equal to 0. And that's where that point is, negative 6 comma 0. Same thing with the 2. All right, now I'm going to do something and then I'm going to erase it right away. All right, so I want you to not follow me. So I'm going to show you something and then erase it because I want you to see that we know enough to get a general sketch of this polynomial, because we know where it intersects the x-axis. We know it's curvy. We know to the left it's going down, to the right it's going up. I could technically just go woo, 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 and be close enough. But do you see the problem with that? Do not write that down. The problem with that is, do I really know that that's my relative max and that's my relative min? I'm going to have to do a little more work before I can do a sketch, right? So I'm going to take away all the green. Hopefully you were listening to me and not just blindly, or well, I guess if you were blindly following me, you wouldn't have seen, but you know what I mean. All right, so we've got to plot a few additional points. We know that to the, let me switch the color, let me just do red. So we know that to the left, so as we're looking to the left of this point right here at -6, we know that the function is going to be heading down. We don't need to plug anything in to the left of -6. But we're really wondering, hey, what happens between -6 and 0, right? What happens? So we pick a point in between there. I mean, can we pick halfway and pick -3? Sure we can. We could pick any of those points and it would help us. But let's go ahead and pick -3. And so what I'm going to do is I could go ahead and plug it up to the top, or I could plug it into the factored form, which might be a little easier. I'm going to plug it into the factored form, especially because I don't have a calculator in front of me. I'm going to have to pause if I need a calculator. So if I plug it into -3, I get what? -3 times, and I'm looking right here at the factored form, -3 plus 6, 6 minus 3 is 3, and then -3 minus 2 is -5. So I'm going to have what? -9 times -5, which is 45. Oh, that's pretty tall. I'm not going to be able to fit it. So we know that in between -6 and 0, I'm going to kind of like go off of the graph, and then I'll come back down. What I could do too, let me see if I can scooch this. Oh yeah, I can. Okay, kind of messes, but what I can do is bring my zeros back down. I'll just go off the graph, and there'll be an understanding between us that, yeah, I know it's really supposed to be 45, but the way my scale is for the y-axis, we're not going to make that. All right, let's see what's going on between 0 and 2. So I'm going to look at 1, right? So let's plug 1 into our factored form, and 1's going to give me what? 1, and then 1 plus 6 is 7, and then 1 minus 2 is -1. So that's going to give us what? -7. Oh, we can graph that, right? When x is 1, y is -7. That's more graphable. Now we are ready. Now I know it's terrible. We're going to say, we're going to put, how about we do this? We're going to put a little cut into our x-axis and then put a dot and say, that's 45, by the way, okay? So, you know, we got to do what we got to do. All right, so let's put it together. Let's put, oh gosh, my -6 went away. Let's go ahead and pick the green. And we know that from the left, we're going down. So we're going to start down here. We're going to come up. About halfway through, we're going to hit 45. We're going to come back down. Uh-oh, I got to pause here. Man, I got to start over again. That was terrible. I have to plot, even though I know the -3, 45, let's go ahead and plot those points. So let's put -3 and 45, and that's going to help me have at least a little target there. And then 1, -7, we actually have that right here. Okay, now here's the goal. Let's go ahead and put this all together in a way that looks curvy and goes through all the points. So good luck with that. I'm not really good at this, so hopefully you can do a better job on your paper. So here we go. I'm going to start down. I'm going to go through that point. Come on, make that point. I'm going to head up. Hit that point. Curve, 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 curve. Hit that point. Curve, curve, curve. Hit that point and head up that way. That wasn't bad for me, okay? I'm gonna say nice job, Miss Overby. All right, so this is what the polynomial looks like. So what did we do? We used our knowledge of polynomials being curved and continuous. We also used our factoring to find the x-intercepts, or the real zeros of the function, and we used our knowledge that this was going to be going down as we looked at the end behavior to the left, and it was going to be going up as we looked at the end behavior to the right. Yay for us! We did something that we couldn't do before this class. Oh, you know what I really did? Let's see if I even came close. Here's the graph. There we go. So here's the graph that I did when I hit Desmos, and yeah, it's not bad. So they literally, went off. I just didn't want to do that because then you'd say, well, wait, that looks like a gap, right? Okay. All right, let's do the next one. So we're going to look at the highest degree and the leading coefficient. So the highest degree is 3. So normally that would mean down to the left, up to the right. But because the leading coefficient's -1, more importantly, it's negative, then we know that's flipped, right? So instead of going down to the left, we're going up as we look at the end behavior to the right, and we're going down as we look at the end behavior as we're going, wait, did I say to the right? Sorry. We're going up as we look at the end behavior going to the left, and the graph is going to be going down as we look at the end behavior going to the right. All right, so we want to go ahead and find the real zeros of the polynomial. We're going to factor out. All right, it says factor out the GCF. There's no GCF to factor out, but we're going to have to factor by grouping this time. And I don't know if everybody remembers that, so I'll try to slow myself down. And so what I'm looking at, also stepping on my mic. So what I'm looking at rewriting the polynomial, and then to find the real zeros, to find the x-intercepts, I set the y value equal to 0 because every single point on that x-axis has y equal to 0. And so then I'm like, okay, I can't, it's not a trinomial, so I can't set my two parentheses. I have to factor by grouping. And this is what it looks like. We're going to group these two terms together and then these two terms together. And we're going to factor out the GCF from each of those two groups. Trust me, we're allowed to do this. And so here we go. I'm looking at these two, and first of all, I'm like, ooh, that negative, I'm factoring it out. Nobody likes a negative. You got to get rid of that. And then I'm looking at these two terms, and the largest thing they have in common, their GCF, is x squared. So I'm going to factor out the x squared. That leaves me with x minus 2. Now, let's go ahead and distribute to make sure we got back to what we originally started with. If I distribute negative x squared times x, that gives me negative x cubed. Negative x squared times negative 2, that gives me a positive 2x squared. So we're good, right? I'm just checking my time. All right, so we're good. I'm going to do the same thing with the second one. I'm going to factor out the GCF, and the GCF is 4. So when I factor out the 4, I end up with x minus 2. Now, here's the deal. We know that we did it right because this and this are the same. Now, if for some reason those weren't the same, we'd have to start over again because that's not going to be helpful. All right, so now what we're going to do is we are going to look at, let's see, we're going to look at this whole term right there because now that's just one term, and this whole term, and we're going to factor out again the GCF. What do those two terms have in common? They have x minus 2 in common. So now what we're going to do is we are going to, let me scooch over here, we're going to factor out an x minus 2, and we're going to see what we have left behind, and we still have it equal to 0. So when I factor out an x minus 2, that's like saying when we look at this first term right here, it's really saying I'm dividing this whole term by x minus 2, right? Because when we distribute, we're multiplying. When we factor out, we're actually dividing by what we're factoring out. We divide the term by what we factor out. If I factor out an x minus 2, that means I just got rid of my x minus 2. What's left? Negative x squared. So we're going to go ahead and put that negative x squared. Once again, if I wanted to, right, I could see going backwards, I end up right back where I started. Same thing here. If I factor out the x minus 2, that means I got rid of it, and I have a 4 left. So if you don't believe me, pause this video and distribute the x minus 2 back to the negative x squared plus 4, and you'll get right back where we started in the very beginning, right here. All right. If this is hard for you, just ask me to put on the blog another factor by grouping video. I'll find somebody who's probably done a 4-minute video and put it on there. Just let me know. All right, so now we can go ahead and use our multiplicative property of 0 because we have something times something equals 0. So we know that either x minus 2 is equal to 0 or negative x squared plus 4 is equal to 0. Okay, so here we go. We're going to add 2 to both sides. We know one of our x-intercepts is right there at 2. And here, I'm going to go ahead and add the x squared to the right side. It's just a little faster. Whoops, that's not what I meant to write. Oh, I hate this big eraser. Let's see. Let's start over again. So what I'm going to do is I'm going to bring that x squared to the other side. I'll do the square root of it. And when I do the square root of it, I've got to remember plus or minus square root of 4. So I'm going to have an additional, well, I already had the 2, right? So I don't need to put another dot there on the 2. And we'll learn more about what that means when we end up with the same 0 twice. It doesn't mean we put a second dot on it. There's just one dot, but we'll talk about that later. But the negative 2, that's a new 0. So we're going to stop and put that there. Yay, we've got our end behavior. We've got our x-intercepts. Now we need to know what goes on between negative 2 and 2. So we're going to go ahead, let's plug in 0. Isn't a 0 a good number to plug in? So we'll go ahead and plug in 0. And when we do that, we can plug it into the factor form part, or we could just even look up here at the original. That's not going to be too difficult to do without a calculator. So 0, 0, 0, negative 8. All right, so one of our points is at 0, negative 8. But I also need to know, I kind of have a question. It's like, I know I'm coming down this way, right? I'm coming down this way. I'll go through I'm sorry, I'm going to do this. I'm doing it with my hand and you can't see it. Once again, I'm going to erase what I'm doing, but I'm just getting an idea of what's going on. So I'm coming down this way, right? I'm going to turn like that. Now, here's the question. I know I can't keep going up. This must be where I hit this point and turn around, right? But we could always make sure that that's what happens. We could always plug in, let's say, a 3. If I did that, oh man, I'd have to do some math, wouldn't I? If I plug in a 3, I'm going to plug it into the factored form 1 right here. 3 minus 2 is 1, so I'd have a 1, and then negative 9 plus 4 is negative 5. So that gives me the negative 5. So I know that right here, I'm on the right path. All right. So actually, that's not a bad graph besides my wiggle. But I'll go ahead and do that again so we can be there together and do it. So we know we added. All right. Why is this not undoing? Okay. Oh, I see what it's undoing. It's undoing a lot of things, isn't it? Okay. I was just very impatient. We had the 1 and the negative 5, right? All right. So, oh, I'm sorry. Was that the 3 and the negative 5? Yes, it was 3 and negative 5. Okay. So the 3 and the negative 5, let's put that down. And now let's go ahead, knowing that polynomials are smooth curves. This one's going, the left-hand behavior is going up, right-hand behavior is going down. Then we know that we're coming down this way. We're going to hit this. We're going to head up. We're going to hit this. And then we're going to head back down. All right. I think this is kind of fun. All right, let's compare this to when I put it on Desmos. Let's see if we look good. And we look great, don't we? Okay. Ooh. Okay. They did something that we probably should have done too, because really right here the graph isn't right. So let's live and learn, because that is what life's about. We did have the y-intercept here, but I assumed we're bouncing here, and now when we look, it's like, no, really our very lowest is going to be at negative 10, it looks like, or a little bit above negative 10, maybe negative 9. So another thing we would have wanted to check out is what's going on between negative 2 when x is equal to negative 2 and when x is equal to 0. Let's plug in a negative 1. That would have been a good thing to plug in just to get a better sense of what our graph looks like. So that's what we do when we plot a few additional points. And I should have been a little more curious. I think I'm just getting tired of talking in this video, so I wanted to be done. Oops, not a good reason. All right, that is not acceptable, Ms. Overby. All right, so let's plug in negative 1. I'm going to use, once again, this factored form to plug negative 1 in. Though I could do it up here, right? It doesn't matter. I'll get the same thing. It just looks like this is easier. Negative 1 minus 2, that's going to give me a negative 3. And then negative 1 squared is positive 1, but then there's that negative weighting. Negative 1 plus 4 is 3, so that is negative 9, just like Desmos had. So when we switch back to the green, we can still keep this going, right? Oh, why did I put a dot on? Oh my goodness gracious. All right. Bear with me. So here we've got negative 8. Here we've got negative 1, negative 9. All right, so we're going to come down. We're going to hit the negative 9. Then we're going to go through. There we go. That's a more complete graph. All right, we're going to move on to something a little different. And I think this is, no, we're going to talk about multiplicity. This is a long, long video. I apologize for it, but this seems to be a very important, well, it doesn't seem to be, it's super important that we get this right. All right, so find a polynomial function with the following zeros. So this is actually a backward problem because usually we're given a function and we're asked to move down and find all the zeros. But look, they gave us the answer. X equals 0, x equals negative 1, and x equals 3. I like doing this problem backwards. Give it a try. If you don't like it, you can do it a different way. But this is how I do it. I say, oh, great, thanks. Thanks for giving me the answer. Now I need to move backwards so I can find out what polynomial these answers came from. Now, note, this way, if we do it all together, we will get the same polynomial. That doesn't mean that's the only polynomial with those zeros, right? I just want to make that clear. We're going to get one of the polynomials that, that would have those zeros. So here we go. If x equals 0, I want to put this back into factored form where, you know, I subtract the 0 and set it equal to 0. I know that was not a good one to start with. But look at this one, x equals negative 1, right? The line before it looked like this. And if you don't believe me, go look at some of the ones we just finished. Here, the x equals 3, the line before it would have looked like this. So see what I'm doing? I'm reconstructing the problem going backwards. This line right here was when we applied the multiplicative property of 0. But where did that come from? That came from the factored form. Now, I agree. I'm not going to write x minus 0, okay, because that's going to look weird. But I'm just going to write an x. But here, I'll write the x plus 1, and then that one's my x minus 3, right? Now, I'm going to go ahead and I have to multiply 3 terms. I'm going to choose to focus on multiplying these 2 binomials first, and when I'm done, I'll distribute that x, all right? You can do it a different way, but that's the way I'm going to do it. So I'm going to go ahead and I'm going to take, a lot of you learned it as FOIL, it's just distributive property, right? I'm going to take this x, I'm going to distribute it. X times x is x squared, x times negative 3 is negative 3x, and I'm done. Well, I'm done with the x. Now I'm going to distribute the 1. 1 times x is 1, and 1 times negative 3 is negative 3. I'm going to go ahead and pull that up here. Oh, and I'm going to combine the like terms. Oops. All right, where did we go? Okay, that was weird. Maybe you followed what happened, but I didn't. All right, so we're going to combine. Okay, it's doing the same thing. Here's what I'm going to do. I'm going to go ahead and erase. Yeah, it's just dangerous erasing, isn't it, on the smartboard? So that's x squared. That was minus 3x, and then plus x minus 3. All right, so we're going to combine the negative 3x plus x. So that's negative 2x. So we'll have x squared minus 2x minus 3. Now, we're not going to forget about that x. We're going to bring the x up. And we could just keep saying equals 0, and we will. But when we really get to the top, we're going to say equals y, right? We're going to go ahead, distribute the x. So we'll have x times x squared is x cubed. X times negative 2x is negative 2x squared. X times negative 3 is negative 3x. I'm not going to write equals 0. I'm going to write f of x equals, or you could write y equals, because we really are answering the question, what polynomial has the zeros of, or has the x-intercepts of 0, negative 1, and 3. This one does, unless I made a mistake, but let's just double check. All right, I just distributed. That looks good. Everything looks good. And so that is the polynomial that has those 3 zeros. Once again, there are a zillion polynomials that have those zeros, but this is one of them for sure. All right. Now let's talk about multiplicity. I said we were going to talk about that later. I just forgot it's in the same lesson. This is a packed lesson, I'm not going to lie. We're going to make it though. How many zeros does y equals x minus 5 squared have, and what does it look like? Well, if we think about the graph, we know that this is just a parent function, that's the quadratic, and it's shifted to the right, the vertex is shifted to the right. We know exactly it's going to have 1 0, right? It's going to have 1 0, but yet Yet, if we did the algebra, if we took the x minus 5 squared and factored it or wrote it as x minus 5 times x minus 5 and used the multiplicative property of 0, we get that actually there are 2 zeros, right? All right, there's really no, there's just one. Okay, I'm not going to pretend that there are 2, but we say that it has a multiplicity of 2, that at this quadratic has a 0 at 5 with a multiplicity of 2. Whew. All right, let's look at what else we have. What about y equals x minus 5 cubed? So we know this is a cubic function. It's going to look different, right? It's not going to be up, up. It's going to be, down to the left, up to the right, and it's going to be shifted. And so it only has one that we can see, but technically, can you see here in the algebra, we're going to have 3. So we would say this has a multiplicity of 3 at x equals 5. So what is multiplicity? It just is acknowledging that there are repeated zeros. And the rule, if you can see this, let's see if I can point out some things. So here, k is our exponent. And as long as k is greater than 1, so we're looking at 2, 3, 4, etc., you're going to have a repeated 0 exactly with the multiplicity of whatever your exponent is. So if you have a binomial, so we're really just talking about binomials, or, so for instance, if our function was just a binomial squared or a binomial cubed, or when you took your polynomial and factored, one of your factors is squared or cubed, then you know you have a repeated 0 at that x with the multiplicity of whatever your exponent is. So we'd say we have a repeated 0 at x equals 5 with a multiplicity of 2. Here we would say we have a repeated 0 at x equals 5 with the multiplicity of 3. All right, this matters when we look at some of the really important theorems for polynomials. So, and another important thing, if it's odd, the graph crosses the x-axis at that repeated 0. So note that the graph at this 0 crosses right through it. But if your exponent is even, then the graph touches, I would say bounces, because that's what it looks like it's doing. It bounces right off of its 0. And yes, you need to know this. You need to know everything I've been saying in this lesson. So how can you remember it? I have a silly way. You know how if you're, let's say you and your best friend are at odds with each other, like I'm going to use terms that I don't know if people use anymore. So if you're at odds with each other, you're just not getting along. You're not in agreement, right? You're at odds. And most likely, if you're at odds with each other, you're going to act cross towards each other. Once again, a term I don't know if we use anymore. If I'm going to act cross to you, it is not pleasant. Okay, it's the opposite of pleasant. It is just, it's cross. I'm going to act mad. And so that's the way I remember odd, well, I remember just because I know, but this is a fun way to remember. If it's odd, then it's going to cross. And then if that same relationship, everything's feeling even, both of you are happy, it's all even, then you're just going to bounce along with your relationship, right? All right, there you have it. I hope this is our last slide. It's been a long time. Yay, we did it. Thanks for joining me, and I will see you in class.